Hello, this is Dr. Zachary Roman, and I would like to thank you for joining me for the multi-level modeling course. Today we will have our second lecture, and today will be an intro to MLM, or multi-level modeling. So we'll start by looking at something called hierarchical data structures. This will be a core component necessary when we conduct multi-level models, and so we're going to focus a lot on this today. We'll talk about something called an ICC, the interclass correlation. We'll look at the formulas for multi-level models, and we'll talk about when and why we use them. Then we will take a look at some software that's available. We'll focus on R and discuss model testing procedures, which is a little different in multi-level modeling than most other frameworks. So first, I just want to get this out of the way. I consult and talk with many academics and researchers who get these terms confused. Multi-level modeling, hierarchical modeling or hierarchical linear modeling, and random effects modeling. For whatever reason, these are synonyms. So I will be using the term multi-level modeling because that's how I learned it, but any of these terms all mean the same thing. So keep that in mind when you're reading literature or you're looking to do a lit review. Some people will use the word hierarchical linear modeling, random effects, etc. These all mean the same thing. From all statisticians to you, I apologize that this is the reality we live in, but this is what we have. So let's talk about hierarchical data structures. Data structures are considered hierarchical if we can distinguish different levels within them. Objects from lower levels can be sorted unambiguously into higher level clusters. So a classic example, and one we'll use a lot in this class, would be pupils or students in classes. And so the students are the lower level object, and classes are the hierarchy. So students can each exist only in one of these classes. And we could continue the nesting further. We could say pupils nested in classes, classes nested in schools, schools nested in towns, towns nested in counties, counties nested in states or cantons, cantons in countries, countries in trade groups in continents, etc. So this is the idea of hierarchy in our data. Each individual can belong to a single hierarchy above them. We could also say employees in a work team, or bugs in a forest under different stones or trees. A bug can only be under one stone or one tree. We could talk about teeth being clustered in different mouths. Each teeth belongs to one person's mouth or animal's mouth, no more than that. However, each mouth can have many teeth. Just as one pupil can only belong to one class, each class can have many pupils. Now, this class is titled Longitudinal Multi-Level Modeling, and so in the temporal or the time-based sense, measurements can be considered nested in subjects. This is a longitudinal hierarchical structure. Now, we will only be doing cross-sectional today. We will not get to longitudinal yet. It's important that we first understand non-longitudinal clustering. So leave that aside for now. That will be the focus of the rest of the course once we move forward to it. In a more formal context, each subject, which we will always denote as I, up until N. So when I say the ith subject, I just mean one of the subjects. In cluster J, we have different types of variables that can be measured. So using our last example, a student would be I, the cluster or the class they belong to would be J. So the J is the higher order cluster, I is the lower order cluster, or just the participants. So in multi-level models, now if you picture this, right, students nested in classes, we could have information about students, right, their IQ or their performance on math tests or how much they annoy their teachers. This would be a global variable. Now notice here, the subscript is very important when we get to multi-level modeling. X sub ij means we have information about the individual in the cluster. So the subscript is important here. IJ tells us within the subject, within the cluster. So this information will come down to the lowest level because it's individual level information, Xij. We can also have structural variables. Notice here that the subscript is just a J. So in a structural variable, this will provide information about the global level variance, right? So this could be standard deviations or correlations about the individual participants at the cluster level. The average IQ of the cluster, for example. This can be included as well. Then we have contextual variables. These will also be common. So if we have students nested in classes, each class will have one teacher. That one teacher might have gotten really good grades in college. And so the teacher's performance, we can summarize with here with a ZJ. Notice again, it's cluster level information. When we have level 1 information or information about every participant, we have a Xij. When we have information about the participants within the cluster, but just at the cluster level, it's Xj, X bar J. And when we have information about the cluster itself, ZJ, okay? So the J, just about the cluster. So let's use that example here. Let's say we want to look at the relationship between pupils or students' math skill, Yij, predicted by individual cognitive skills, Xij. Again, Y will always have information regarding every case. Xij, we're saying we will have cognitive skills for each participant or each student. And we will have the teacher's didactic skill, which will be Zj. Just think of this as some performance measure of the teacher's ability. So each cluster will have each teacher will have a didactic score. So data comes from the classes, each with a different teacher from which students are sampled. Aggregation. Individual data can be summarized for each cluster, right? So we could have a model where we're estimating the average, the Jth information, right? So the average math skill for the class would be Y bar J. And we can predict this by the average cognitive skill within the class. And then the teacher's didactic skill. So notice here that the sample size of this model will be the number of classes we have. This will not be the number of participants because we are simply using an average math skill, which is what we're predicting, by an average cognitive skill of the class. Now, I think we can all see that that's pretty problematic, right? We're losing a lot of information by simply taking averages from the class, although in theory this would work. Here's the problem. We lose a lot of sample size because we're reducing the amount of information to averages. Because of that, we also lose power. Power being our ability to accurately accurately accept a true null hypothesis. We also have something called the ecological fallacy, which is interpreting aggregated data on an individual level. In an analysis such as this, we should not extrapolate the types of claims we make to the individual because we are actually only making estimates at the class size level. This is a problem, and this is where multi-level modeling will come in. Another issue here, and just to clarify, this is not a model we should be running. This is just a theoretical way of motivating multi-level modeling. We never want to reduce our information. We don't want to drop our sample size just to fit things into a model. And so multi-level modeling will come to the rescue here. But first, let's point out another problem. Cluster information is going to be assigned to each subject and hence multiplied. So the alternative option, if we're sticking to a regression framework here, is that now we have each individual's value, y sub ij, and each individual's cognitive ability, so math, cognitive ability, but now we have to force z to have an ij subscript. What does that mean? Well, because each teacher is teaching, some amount of students, we can't, the z value in this framework will be the same piece of information repeatedly presented so that we can fill the whole column here. So the matrix algebra is stabilized. This Z needs to have a length of n. And so what we end up doing is we end up just multiply representing the same piece of information. And now we have the opposite problem. So in this case, when we are aggregating data, we end up with power loss, which means problems with type 2 error rates. When we disaggregate, we have problems with type 1 error rates. We get an inflation due to spuriously small standard errors. The standard error associated with this term here will be much lower than it really should be because we're over-representing the amount of data that is present. This is an issue. Now, another problem comes into play here, which is the atomistic fallacy, which I've always known as Simpson's paradox, which is interpreting aggregate data on an individual level. Let's take a look at what Simpson's paradox looks like here. So here we have just a random plot where we have some dosage of a drug on the x-axis and then some recovery probability on the y-axis. So you can see here that the dotted line would be the regression equation if we didn't take gender into account. This would be the slope here, saying that as dosage goes up, the probability of recovery is going up as well. But take a look at what happens when we desegregate the data. So when we actually take a look at male and female separately, we actually have a decreasing relationship. As your dosage increases, your recovery probability is actually going down. This is Simpson's paradox, and it provides us with a strong motivation to represent all the information we can about our data, because any further breakdown of the data could simply result in a complete and utter change to the relationships that we are observing. So how does that relate back to this? Well, by not taking into account the individual clusters here and treating information as multiply represented by the teacher, we could, in fact, by not taking into account the different classes, result in a paradox of Simpson's. It result in a Simpson paradox here. If we think that each of these could be a class, maybe classes individually are going down, but some just have different means, which result in a Simpson's paradox. We could claim a positive relationship. In reality, we could have a negative relationship. Okay, so we know we have data situations in which cases are clustered together. Solutions for aggregation and disaggregation do not work. We either inflate our type 1 or type 2 error rate and have other problems. And so let's talk about multi-level modeling and how it accomplishes a solution to the clustering problems that we see here with aggregation and disaggregation. So let's start with something called the intra-class correlation. If data is hierarchical, typically multi-level modeling will be the best method to analyze the data. This will circumvent the problems of aggregation and disaggregation. However, we're going to talk about parsimony. Multi-level models are not always necessary because they might be too complex. Parsimony, or simplicity, is desired in science, and there's not an exception for this with our statistics. We want to use the most simple model that accurately represents our data. So let's look at an example here. Individual math skills measured in classes will likely also depend on characteristics of the classes. Therefore, an MLM would likely provide us with an appropriate means of measuring this clustering. For a counterexample, students' parents' interest in basketball could be completely independent of their children's class membership. We can aggregate all of our information that we collect into hierarchies, no matter what I'm researching, even if it's personality features. I could always sample from, different cities and states and countries and regions and produce hierarchical data. But that does not mean that the hierarchy is necessary in understanding the information. The good news is theory can help us come to a conclusion if we need to do this, but we also can quantify the amount of clustering, which gives us an indication if MLM is necessary or if it is too complex. So we will look at the inter-class correlation, which quantifies this, and I'll be calling it the ICC. The ICC measures how similar subjects within a class are compared to subjects outside of a class or hierarchy. So let's do a thought experiment. Math skills are measured for random subjects I in different random classes J. If we repeatedly select two subjects, I and I prime, two different subjects, at random from the same J class, and we plot these pairs of points. If math skill depends on class membership, then the correlation between all points across the classes will be high. If math skill is independent of class membership and likely due to other individual characteristics, then the correlation between all points across the classes should be low. Let's see what this looks like visualized. So if we take random pairs of pupils within classes and we look at the correlation between these, we should see that if the ICC is large, we'll see what we see on the left here, a strong relationship, and it will be positive. We see that the different classes are more similar within one another. If the ICC is small, like we see on the right, you'll see that class membership does not really play a role in the relationships between the points. Arguably, individual characteristics are making up the differences that we observe. So let's take a look at the very first multi-level model we'll discuss in this class. In order to estimate an interclass correlation, or ICC, we assume the following model. The observed score, Yij, we could call this math, and remember Ij, so an individual nested within a group, is decomposed into multiple components. An average overall component, this is gamma 0, 0. This will be the average of Yij. A cluster specific centered component, Uij, so this will be cluster specific means. And then an individual component, which is epsilon ij. So we see that these two components together, gamma 0, 0 and U0j, are the fixed slope, or B0j. This is a cluster-specific mean for the variable. So together, these are the cluster-specific mean for each variable. The variance of the observed variable is then, the variance of y, is the variance of gamma 0, 0, plus U0, plus the unknown, epsilon. Under the assumption that U0 and epsilon are uncorrelated, we can take this term. And this is plausible, assuming that individuals were randomly sampled from the clusters. So how do we estimate the ICC? Based on the model, two variance components can be estimated. The variance component due to the clustering, or the variance of U0, which is the between cluster variance. The variance component due to individual differences within a cluster, this is the within variance, is the variance epsilon. So the variance of U0 is going to be sigma squared U0, and the variance of epsilon is going to be sigma squared epsilon. The ICC is thus defined as the variance of the between subject clusters, so the between cluster variance, divided by the between cluster variance plus the within cluster variance. So what we're doing, similar to R squared here, is we're dividing the known variance due to the cluster by all variance here. This will always range from 0 to 1. The higher the ICC, the stronger the variance of the observed variable reflect the variance of the cluster membership, aka, or also known as, the clustering is stronger. A higher ICC suggests that the groups are more similar within one another, and between the groups there are relational differences with the outcome. If the ICC is greater than 0, we should use an MLM for data analysis. This can get a little tricky. You will see different rules of thumb. You will see some people say 0.05 and above. You can also see very high ICCs. It really just depends, but the best practice would be, if the ICC is greater than 0, we should use an MLM. The higher that is, the more regression will be biased in its estimates because we cannot account for that clustering in regression. So that is how we assess if we need to use a multi-level model. Now, let's take a look at a standard model. In MLMs, different levels are distinguishable. So for example, the level 1, this will be in the cross-sectional examples we're using now. These will just be the subjects. Each subject has an individual score. Level 1 is that level. So if we have subjects and classes, level 1 is the individual students. Level 2 would then be the classes. So all of these students each belong to a class. Now, multi-level models can have many, many levels. So in theory, we could have another higher level. So classes could be nested within schools. That would be level 3. And schools could be nested within school districts. School districts could be nested within cities or countries, etc. So we can have many, many, many levels of a multi-level model. So variables are measured on different levels. Y, which is our criterion, or outcome variable, or dependent variable, all the same thing, will always be measured on level 1. So we will always, to use multi-level modeling, we need a unique score for every individual at the individual level, or at level 1. Predictor variables X and Z can be measured on different levels. If X is measured on the same level as Y, it will provide individual information about every single subject. Z can be measured on higher levels and refers to cluster-specific information. Using this example, with subjects, we could measure an outcome variable of grade point average, or your average grade in school. Each classes, we could have higher order measurements of teacher performance, and even higher, we could have variables for school funding, or the amount of money the school gets. So we can measure variables at each level of the multi-level model. So now we have our first model. This will be called a random intercept model, and I'll break that down for you. So in multi-level modeling, each level can be broken down into an individual equation. So we have the level 1 individual level equation. This will always have subscripts for the amount of levels we have. I is the individual level, J being the second level, so the cluster level. B0J is going to be a random intercept. So this will be an intercept representing class-specific information. B1 is going to be our slope. This is just a fixed effect. It is just like regression, where the slope summarizes the average relationship between X and Y. And then we will have our unexplained information, epsilon. Now, the additional terms. Our intercept is broken down into multiple terms. Remember from earlier, gamma 0, 0? This is the average intercept across all subjects and clusters. So this ignores the clustering information and just gives us the average intercept. However, U0J is the cluster-specific deviation from an average intercept for the Jth cluster. So this tells us the deviations that clusters are, on average, on the intercept from the fixed intercept here. So let's take a look at what this looks like. Gamma 0, 0 will be right here. And I apologize, it looks like my typesetting dropped a few symbols here. This would be gamma 0, 0. So this is the average intercept from each cluster. And so each slope here is a participant, okay? And so gamma 0, 0 plus the cluster specific deviation from that group provides us with the other individual slope, or well, the other individual intercept. We're just doing intercepts here. So we're just looking at where these deviate with 0. Now, the variance of the differences here in these intercepts, U0, is the addition we get with the random intercept model. So, for example, If these intercepts were all very close to one another, this would be low. If the clusters all have very different intercepts, the variance U0 will be high. So what we're saying here is we have this average regression model, but we're decomposing the intercept into multiple terms. We now have gamma 0, 0, which is the average intercept. And then we have a variance around gamma 0, 0, which tells us on average how much each of these clusters are deviating from the average. Now let's look at what the model looks like via substitution. So taking this formula and substituting these two terms in here for B0J results in the full formula. So this is the one formula that represents both levels. So we're now going to make a distinction here between something called fixed and random effects. In this breakdown, we have our dependent variable measured for all participants. Gamma 0, 0 is considered a fixed intercept because it is the intercept or the expected value of y when all variables are 0 for each of the classes. So this is just an intercept, just like you're used to interpreting in regression. This slope, again, is the average slope of the x variable related to y. Again, just an average slope, nothing different. These terms are just regression terms. But now what we include as well is a variance term here for how much the fixed intercept is varying between groups. Again, we have our error term. So I'll talk about that through one more time with the slides here. Our fixed parameters are gamma 0, 0 and B1, the slope. So the fixed intercept tells us the average score, the expected value of y when all predictors are 0. This pays no regard to the cluster. Same with the slope here. This is the relationship between the x and the y variable regardless of cluster. The random parameters here is just the variance of U0. This contains all the deviations groups each cluster is from the fixed term here, and the variance of it is what we estimate. And then of course the residual parameter as well. So let's talk about characteristics of the random term. U0 is conceptualized as a random term in the same sense as the residual epsilon. U0 is a random cluster-specific deviation from the average intercept, which is gamma 0, 0. It is assumed that U0 is going to be uncorrelated with epsilon, and that the predictor variables, of course, x here. We don't want multicollinearity induced. U0 is assumed to be normally distributed with a 0 mean, okay? All right, so now interpreting our random intercepts. Depending on the variance of the random intercept, subjects across clusters are more or less different from each other. If the variance of the random intercept is large, intercepts of the clusters vary a lot. If the variance of the random intercept is small, the intercepts of the clusters are similar. Now, in this model, it is assumed that the relationships between the predictor and the criterion is the same for all clusters. The slopes are parallel. If this assumption is not plausible, we can include a random slope parameter, which is what we'll get to next. But I want to talk about this with the image one more time. So, if U0 is small, these intercepts will all be very close to one another. The larger this is, the more dispersion we see in the intercept. Another way to put that is, we would expect there to be more of a difference in the anticipated y value when x is 0 for each cluster. Okay, so, and note when I say that the slopes are assumed to be the same, notice how in the random intercept model, all the slopes will be estimated to have the same value. We do not include any randomness on the slope here, therefore we only have a random intercept term, and all we're considering is the variance of the intercepts across clusters. So now let's look at a random intercept, random slope model. Notice that we have our same individual level regression model, and now we have another level 2 cluster model for the slope of x. So this expands a little bit. Gamma 0, 0 is still the average intercept across all clusters, and U0j is the cluster-specific deviation from the average intercept. So this is the deviation from here. Gamma 1, 0 is now our average slope across all clusters, and U1j is going to be the cluster-specific deviation from the average slope. Now B1j is called our random slope. Okay, this gets a lot bigger as we substitute this model in. So let's go ahead and take a look one more time. Through substitution to produce a single equation, B0 here is multiplied by nothing, so we simply take both of these terms and they're added in replace of B0j here. But because B1j is multiplied by Xij, we need to do some substitution here. During substitution here, we'll end up with more terms. We need to multiply gamma 1, 0 times Xij, and we also need to multiply U1j by Xij. So notice how this term ends up, how the full model ends up. We have a fixed intercept, a fixed slope multiplied by our variable. We have a random intercept, which tells us the deviations that clusters are here from gamma 0, 0. And then we have U1j, which tells us, again, the variance of the slopes. So this is telling us how much the clusters deviate, the slope of the clusters deviate from the average slope. So our fixed parameters are gamma 0, 0 and beta 1. These are our average slopes. The random parameter, variance of U0, variance of U1, and covariance between U0 and U1 are now in random parameters in the model, and of course our residual. Now I haven't introduced this idea of the covariance between the random effects, but we'll get there soon. While this is not shown in the model, it is typically estimated and very informative. So when introducing additional random terms in the model, it is necessary to carefully specify the covariance matrix of these terms. This is very important. So bold U here, or the matrix of random terms, U0 and U1 prime, is bivariate normally distributed. So we have a multivariate normal distribution here. Depending on the model, different restrictions can be made on this matrix. We can constrain the covariance between the random effects in different ways to help us accommodate complexity in the model. So let's take a look at illustrations of the random slope. Notice now that the slopes differ. So gamma 0, 0 is the average intercept. Each of these intercepts, this is the average of all of these intercepts here, or where they're crossing 0. Gamma 1, 0 is the average slope. So when we take all of these slopes, the average slope is right here. Now, each case will have an average intercept. In the random slope, random intercept model, we will have a fixed intercept here, or average intercept, plus the cluster-specific deviation, so this one's higher, and it will also have a fixed slope plus the cluster-specific deviation. So now what we have is different slopes and different intercepts for each model. We also have this term that we include, which is the covariance, or the correlation, between the random intercept and the random slope. In this case, it's 0. And I'll show you what it looks like when it's positive. So when it's positive, what we are learning here is that as the intercept gets higher, the slope increases. This is an important term for us, and it tells us the relationship between the random terms. A positive correlation or covariance between U0 and U1, random intercept and random slope term, tells us as the intercept goes up, the slope is increasing. If this is negative, it will tell us that as the slope is going up, or as the intercept goes up, the slope goes down. So some cool examples for this. In a longitudinal sense, if students are in an advanced math class, the higher their starting value or the more math knowledge they have, the higher they will develop. But if someone comes into an advanced math course with very little math knowledge, they won't see as much development across time. That is what this covariance term tells us. Alternatively, if it is maybe a remedial math class or a class for people who are behind, we could have a negative covariance here, where if you have a very high score, you'll see no development, but people with low scores will see more development. This is what the covariance between the random terms tells us about the clusters. So let's interpret. The variance of the slope, or the variance of U1, indicates how strongly the regression lines vary across clusters. So the higher the variance of U1, the more the slopes are different. If it's very similar, or if the variance is very low of U1, then the slopes will all be very similar. The larger the variance, the more heterogeneous are the cluster-specific slopes. We just mean the slopes are more similar when the variance is low, and the slopes are more different when the variance is high. If the variance of U0 is very large, the meaning of the average slope is reduced because one cannot assume a similar pattern of the relationship between predictor and criterion variable across the clusters. It can be problematic if we have very high variance. This means that some clusters have negative slopes, some are very high, and it's hard to interpret the meaning of the average slope because we have so much variation. The covariance or correlation between the random terms, the random intercept and random slope, indicates if a systematic relationship exists between cluster-specific intercepts and cluster-specific slopes. To talk about this one more time, if we have higher intercepts related to higher slopes, this is telling us that this covariance is positive. If the higher the intercept, the lower the slope, it is telling us it is negative. In this case, we see zero relationship here. There's no systematic relationship between where the intercept lies and the slope. All right, so plugging in the level 2 equation into the level 1 equation results in our full equation here. So we have the intercept for cluster J, the slope for cluster J, and then the variable here. So distributing this, we result in this full equation. However, in R, fixed and random parts will be specified separately. We won't have to denote this entire equation in this way. However, in HLM or M+, two other pieces of software, you have to specify the level separately. I will not be discussing or using this software much. It's an option that costs money. I use R. It's open source, and I think it has more of a future. So we will focus on R and implementations within R. So let's talk about explain variance. The scope of any regression model is, well, the goal is to explain the individual variance of a dependent variable. This explanation is conducted by introducing new variables or functions of variables. If the random intercept variance or random slope variance is large, then one only has the information that some of the individual variance is explained by membership in a cluster. It remains open what exactly is responsible for these cluster-specific variables. Introducing level 2 variables like zj or x bar j allow us to explain cluster-specific variance. Hence, the next scope in MLM is to explain the cluster-specific variance using additional predictor variables at the cluster level. So now let's take a look at a little bit more of a fleshed out equation. So now, instead of just accounting for variances of clusters, we actually want to explain variance at the cluster-specific level, either an intercept and a slope. The variance of the random term should then decrease. So effectively, if we estimate it without any level 2 variables, we'll just know if there's a high random effect that either the intercept or the slope is varying as a function of the clustering, but that doesn't mean we understand why. That's where more and level 2 variables come into play to help us explain that variance. So here, we've now introduced variables at level 2. Using our classroom example, YIJ could be our math test outcome. XIJ could be the cognitive skills. Again, every student has the math skills and cognitive skills measured. But now we could take teacher-specific ability here and add it to our equation. This will help us decrease or understand where the cluster-specific deviations or variances are coming into play. All right, this brings us to estimation. Multi-level modeling has a little bit of complication in how we estimate our models. Typically, 2 methods will be used: maximum likelihood and REML, restricted maximum likelihood, sometimes called residual maximum likelihood. We'll talk in more detail there. So in maximum likelihood, simultaneous estimation of fixed and random parameters will happen, and we will use this to test the significance of the fixed effects. In REML, however, first estimation of fixed parameters occurs, then random parameters are estimated conditional on the fixed parameters, treated as if they are known. It's got unbiased estimation of random effects, biased estimation of fixed though, so we only use it to test significance of the random effects. We will get into detail on estimation as we move forward. All right, so let's talk about some characteristics and assumptions made here. Sequential random sampling. This is when clusters are sampled randomly. Within each cluster, subjects are sampled randomly. This is optimal. So this is the idea that we would randomly pick, K schools in a country and randomly pick them, and then randomly sample students within each of those schools. This is sequential random. First, we randomly sample the clusters, then the participants. The number of subjects within each cluster can vary. We do not need them to be all the same. And some assumptions for ML and REML are similar in regression analysis. We will focus on the fact that we have normality of the residuals and the random terms, and we have to assess homoscedasticity of the residuals and the random terms. And again, we're using linear models unless we account for curvilinearity in some way. Model building strategy. So there is a lot of different methods and approaches to multi-level modeling that we need to test. Do we need a random slope? Do we need a random intercept? Do we need neither? What do we do? So first, of course, we should estimate our ICC and determine multi-level modeling will be useful. If our ICC is greater than 0, we will start with a saturated model in the top-down approach, where all relevant predictor variables, all relevant interaction effects, and all random effects are specified. So we have all of our variables and interactions. We also have a random intercept, a random slope, and the covariance between the random intercept and slope. Then, using REML, we test which random effects are necessary. Once we decide on the random effects structure, we test which fixed effects are necessary using ML. We run a final model using REML, and then, of course, interpret our results and conduct a residual analysis to assess normality, homoscedasticity, and linearity. So here I say we test the random effects. Well, how do we do that? So remember in our regression lecture that I talk about testing a restricted and unrestricted model with a likelihood ratio test. There we talked about changes in R squared. Here we'll do a likelihood ratio test. So our reference model will be considered M0. In the top-down procedure, this is unrestricted model. This will have all of the random fixed and procedures like this. It has more parameters, so it is less parsimonious. We will have a nested model, M1. A model is nested within another model if it has all of the same effects with less. So it will have at least one less variable in the model, or one less parameter, like a random slope or intercept. So it will always have fewer parameters, and it must be nested. We cannot introduce a new variable into M1. The hypotheses. Our null hypothesis will be that the nested model fits the data equally as well as the reference model or the unrestricted model. So again, what we're saying here, in other words, is that removing a random effect or a variable from the model will not result in any difference to the model. The model will fit the data equally well. And of course, the alternative there is that the nested model fits the data worse than the reference model. It's important to know that this is a directional hypothesis. By removing information from the model, it can never explain the data more. So it will only be worse or equal to. So our null for the likelihood ratio test for comparing an unrestricted and restricted model is that the restricted model with less parameters or variables has the same explanatory power as the reference model. All right, so now I'm going to show you the likelihood ratio test for comparing models. Don't get too caught up in the math here. What's important is that we understand what's happening. Each multi-level model provides something called a likelihood value, also called deviance, and we'll call this L. This gives us an indication about how well that model fits the data. The more the likelihood deviates from 0, the worse is the fit. This likelihood value is used to compare models. So delta L is called the likelihood ratio test. In statistics and mathematics, typically delta is a symbol we use to represent difference. So when I see this, I see difference in the log likelihood. So difference in L is called the likelihood ratio test. It is chi-square distributed with degrees of freedom equal to the degrees of freedom from the restricted model, unrestricted model, minus the degrees of freedom from the restricted model. Effectively, it's just the difference in the number of parameters. Okay, so what's going on? Well, we're just taking the log of the restricted model divided by the unrestricted model times -2. This is the -2 log likelihood ratio test. And if this is significant, it tells us that the removal of the term we use in the restricted model has led to a significant change in the likelihood ratio, or how well the model fits the data. So if the null hypothesis about a random parameter lies on the boundary of the parameter space, a different version of the likelihood test needs to be conducted. So this is for bounded random parameters. And let's think about this. The parameters we're interested in estimating here, which is the variance, here I have the variance of the random intercept. So the random intercept, it cannot be less than 0. A variance term tells us how different the data are. At 0, the data are all the same. Greater than 0, they are different. We cannot have data with a negative variance. Therefore, random parameters need to use a bounded likelihood ratio test. And so if we want to test a model with a single random intercept, we would use the null hypothesis that that variance is equal to 0. The random intercept is 0, therefore all clusters have the same intercept. The alternative is that the variance of the intercepts is non-zero, but it has to be greater, so greater than 0. So the test statistic, delta log likelihood, has a mixture distribution and it has a weird shape. It has a 0.5 chi-squared, 0.5 chi-squared distribution. So it's an odd test. We're simply taking the chi-squared value of the unrestricted and the restricted models, multiplying them by 0.5 and summing them. If one tests a random term in a model with two random effects, the two parameters are tested simultaneously. So in other words, I could have a unrestricted model with random intercept and random slope to a model with no random intercept and no random slope. And in that case, our null hypothesis is that both of the terms are zero here, that there is no random effect. This would mean that the slopes between the clusters are the same and the intercepts between the clusters are the same. And the alternative, of course, is that one of these parameters is greater than zero. So delta L has the distribution of the half chi-squared we just talked about for the p-value derivation. This is the procedure that we will be using to test random effects within this class. When we get to R, I will show you that in action. Information criterion. The information criteria allows you to compare non-nested models that are applied to a data set. By all means, using the AIC, ACI information criterion, in the Bayes information criterion, BIC, these are not as desirable as the log likelihood test, but they do allow us to compare models that are non-nested. So the criteria is based on model fit, but also on model parsimony. So we take the -2 log likelihood plus 2 times the number of parameters here. And in this one, we multiply it by a penalization factor, ln. Well, we take the natural log of n here. These both give us information value about how the data fits the model, how the model fits the data, model fits the data. And smaller values indicate better fit. So these will also help us in the model testing decision making. But there are no rules of thumb or significance test about a substantive difference in AAC, BIC values. So we can only compare them absolutely. So let's summarize today's lesson. When analyzing data with a multi-level model, we need to take care of the following points. First, we should estimate the ICC. And this will indicate if the clustering of the data implies cluster-specific variances that need to be accounted for by a multi-level model. We then will test the random effects first using REML. If the variances are not significant, determined by nested model testing, they should be removed from the model in the name of parsimony. After we've determined the random effect structure, we test the fixed effects. First, removing non-significant interactions, then non-significant main effects. We interpret the model and conduct a residual analysis on both of our residuals to make sure we are not violating assumptions in our model. That's it for today. Thank you for joining me, and you've now covered the basics of cross-sectional multi-level modeling. Have a nice day.